thanks. Yeah, so we're delighted to have Kwang-Sung Jun here today to speak to us. Kwang is an assistant professor in the computer science department in the University of Arizona. Prior to that, he was a postdoc with Francesco Orbona at Boston University. And before that, he spent quite a bit of time in University of Wisconsin at Madison. Today, he's going to be talking about their new paper, Crush Optimism with Pessimism, about some work on structured bandits. So over to you, Kwang.
Okay, hi. Thanks for coming, and yeah, I'm glad to have a chance to share this paper with you guys today. So this is joint work with Chicheng Zhang at the same university, the University of Arizona. Okay, so let's get it started. All right, so this is about structured bandits. So we are given an arm set and the hypothesis class F, and each hypothesis assigns mean reward values for each arm. For example, you can consider the linear case where the arm sets are d dimensional vectors, and the function class is just linear functions. So I tend to think of this as some sort of the set of possible configurations of mean rewards. So before the game starts, the environment chooses F star from F, but this is unknown to the learner. Now for time t1 to n, the learner chooses an arm A, T, and then the environment then generates the reward as a noisy version of F star of A, T. And then the learner only observes the noisy version of that reward. Okay, and the goal is to maximize the cumulative reward, or to put it another way, minimize the cumulative regret. So this measures in expectation the difference between the learner's cumulative reward and that of the oracle who knows F star. Just to put things in context, this is fixed arm set setting, so it's non-contextual. It's fixed, the arm set never changes. And we assume realizability, right? Because we know F star belongs to the already known class F. Okay, this is different from being being agnostic. Okay, so why is this relevant to reinforcement learning seminar here? Lots of techniques here may transfer to RL. For example, it was applied to ergodic RL 2 years ago. And just to think about the problem, of course, you can still use UCB, ignoring all the structure. And then you get this rate of instance-dependent regret bound, which is K over delta times log n. K is the number of arms. Delta is the gap between the best mean reward and the second best mean reward. And you can see that the regret scales with the number of arms. But you may realize that because you have the structure information, script F, ideally, it should really depend on the complexity of the hypothesis class F at hand. So indeed, asymptotically optimal instance-dependent regret is well defined. For example, for linear bandits, it's something like C star times log n, where C star is some well-defined constant. And depending on the instances, it can be much, much smaller than K over delta. And also, it may not even scale with K. Okay, so that's the cool thing about structured bandits. So overall, the goal of this paper is to achieve the asymptotic optimality with improved finite time regret for any function class F. Here's a small note. The worst case regret is beyond the scope. We will focus on instance-dependent regret. Okay, so what's out there to improve? Let's first talk about some backgrounds. Okay, so asymptotic optimality. So this has gotten popular in recent years, and the background is as follows. We've loved optimism in the face of uncertainty principle. And so we have UCB, Thompson sampling, these algorithms. And it seems to be the right thing to do in the unstructured case because it achieves asymptotic optimality, and it also achieves optimal worst case regret. Okay, but what about the structured case? So in the structured case, let's say linear bandits, optimism principle does get you to the optimal worst case rate. That's roughly d root n. How about the instance-dependent asymptotic optimal regret? Turns out the answer is no, and that's the paper by Tor and Chava about this fact. So what's going on here? Let me give you an example. Imagine you're selling fruit, okay, and then you have lemon, orange, and apple nicely embedded into 2D space with sour dimension and the sweet dimension. And imagine that the mean rewards are defined by this simple linear function. So here the best arm is apple. So suppose I'm selling fruit in the following way. I recommend a fruit to you, and then you taste it and you'll buy it if you like it, okay? So in this setup, if you use UCB, it'll recommend orange and apple equally for a very long time, or not equally, but almost equally. So it'll take really long time to identify apple and then commit to apple, okay? Not totally commit, but yeah. Anyways, but if you're a little smarter, you may try out the lemon, which is usually not so popular, but you can try out lemon and see how much people dislike it. And if they really dislike it, then you can start recommending apples only, okay? So it turns out you can use lemon to maximize reward, because it tells apart between whether orange is the best or the apple is best much quicker. And that's exactly what asymptotically optimal algorithms should behave. Okay, so let's look at a little more detail on the lower bound. So what this lower bound says is the regret has to be something like some C of f star times log n. And C of f star is a solution of the optimization problem as follows. I'm not going into detail at this moment, but I will come back later and then explain more detail. But something to point out here is that there's this variables that are being optimized. And these are some sort of the ideal arm pull count, like sample assignments that you should do. So to be optimal, you must pull arm A like gamma A times log n times. In the previous example, the optimization solution will be 8 for the lemon, but 0 for the orange. So it suggests that you should use lemon to do exploration. And once you identify which one is the best one, then you play the apple. And here, we see that orange receives 0. So here we call this lemon as the informative arm and orange to be uninformative arm, okay? Because it doesn't receive a positive value here. Finally, when C of f star is 0, then in most cases, you can get bounded regret, meaning that the regret bound does not scale with n. Okay, so what are the existing algorithms? Well, there are quite a few, but mostly they do something called forced exploration. So what it does is that it makes arm pulls so that we can ensure every arm's pull count is an unbounded function of n, but this has to be lower order than log n. So people use something like log n over 1 plus log n. But then if you do that, then the regret bound at best will be something like this, where the first one is unavoidable term, because this is the one from the lower bound. And the second one is k times some growing function of n. Now, there are two issues. K directly appears in the regret, so you scale necessarily linear with the number of arms. So what if k is like exponentially large? Okay, second, in this case, we cannot achieve bounded regret even if C of f star is equal to 0, because the second term still grows with n. Okay. By the way, I want to mention that there are some parallel studies that avoid forced exploration, but they tend to still depend on k. Okay, so to get around this issue, our research question is as follows. Let's consider a simpler case of the script f, the hypothesis class, being finite. Can we design an algorithm that first enjoys the asymptotic optimality, second, adapts to bounded regret whenever possible, and third, does not necessarily depend on k? To answer this question, we propose a new algorithm, crush optimism with pessimism, crop in short. So some features: no more forced exploration, and the regret scales with k, not with k, but with k of psi, an effective number of arms that we define later, and which can be smaller than k, and sometimes is something of logarithmic of k. And also, you'll see an interesting log n term in the regret that we show it's unavoidable. Okay, so this is roughly the overview of where I'm headed to. So now let's talk about some of the backgrounds. But before then, I don't know if there's any questions.
No, it's all very clear. Or maybe Java.
No, I don't think. I just wanted to say that we didn't see any questions yet. So you're good to go.
Okay.
Okay. No. There is one question.
Okay.
Actions that need to be finite.
Yeah, I must mean finite.
Yeah. So what would you do if it's not finite?
Yeah. I don't know. I'm mainly focused on just finite arm set.
Maybe we can discuss later.
Yeah. Cool. Thank you.
Okay. So that was another very quick question. What do you mean by log n unavoidable? It appears in a lower bound.
Oh, yes. Yeah. You'll see that there are certain arms that you have to pull log n times. Okay. Yeah. You'll see the example. So there's an example I prepared. We can go through. Okay. So let me proceed. Here are the more detailed setup. So for the noise model, I assume one sub-Gaussian noise, but in the paper, it's generalized to sigma squared sub-Gaussian. And some notations, A star of F, that's the best arm predicted by hypothesis F, and mu star of F is the mean reward of the best arm. And we say F supports arm A when A star of F is equal to A. And we say F supports reward V if mu star of F is equal to V. And one more assumption, we assume that every hypothesis F has a unique best arm. Okay, this is really simplifying assumption because it makes our life easier. We do believe that we can extend it to, we can relax the assumption, okay? But it'll tend to make things longer, so yeah, I focus on this case. Okay, so let's first understand this notion called competing hypothesis. Okay, this is an important concept we should understand. This competing hypothesis is relative to a given true hypothesis F star. And these are the set of hypotheses that first assigns the same reward to the best arm. So in this example here, we have 3 arms, and each hypothesis is assigning mean reward values to those arms. Let's say F star is F4. So then the best arm is arm 1 with the mean reward 0.75. So those that qualify the condition 1 over there is the purple line and the red line. So let's look at the second condition. It says it should support a different arm than the best arm. So here, this purple supports the same arm, so this is not qualified. So the competing hypothesis is F1. And the reason why this is important is that this is the presence of competing hypotheses is exactly why you get log n regret. To see why, somehow, let's say you successfully estimated the F star, the true one. Now you have to start doing exploitation, right, to minimize regret. But if you keep getting samples for arm 1, then you get sufficient statistical evidence to reject other hypotheses, including the green, gray, and yellow, but not for the red one. But red one is something that recommends a different arm, right? So to guard against the case where F1 is actually the true one, you do have to sample arm 2 and 3 frequently enough. And how frequent? That's log n. And so you have to pull this thing log n, and that's why this arm pull is transferred to the regret bound, and that's why we get log n regret. Okay, so this is why the competing hypothesis is important. Okay, ask any question if this doesn't make sense. Okay. Okay, so let's just look a little more closer to the lower bound. So let's assume Gaussian reward. So our algorithm will have a regret bound for sub-Gaussian rewards, so reward upper bound, or the regret upper bound. But to claim the optimality, we look at the Gaussian rewards, okay, which is natural. And again, the regret lower bound is something times log n, where that is written as an optimization problem. So let's decipher this one by one. So here we have, let's look at this bottom equation here. So for each competing hypothesis, we have this constraint. So I call this information constraint, right? So we're looking for gamma. So think of gamma as some sample count. We're looking for gamma values for which, when you multiply with the KL divergence between two Gaussian distribution, one located at f star of A, another one located at G of A, right? So if the KL divergence is small, then you have to spend a lot of sample to satisfy this inequality. On the other hand, if this KL divergence is large, we don't have to spend large sample to satisfy this inequality, okay? So in short, you need to find those gamma that will sufficiently distinguish yourself from all these the competing hypotheses. But among those things that satisfy this constraint, you want to be reward efficient. Okay, so that's encoded into this objective function here. And here, this delta A is the gap between the best mean and the mean reward of arm A. Okay, so you want to have assign gamma that has small reward gaps. Okay, so that's the solution. So this is finding most efficient solution that can eliminate the competing hypotheses. Okay, so that's roughly how lower bound is composed. And now let's look at what the lower bound tell us. Okay, so here's an example. This is also an important example. You should ask questions if this doesn't make sense. Okay, so first we have base arms. There are K0 number of them. And the mean rewards are either 1 minus epsilon, 1 or 1 plus epsilon. And each hypothesis have those values, right? And imagine epsilon is something like very small, 0.00001, okay? So the most mean rewards here looks pretty much similar to each other. But we have this extra cheating arms that are log 2 of K0. So these are taking binary values, either 0 or lambda, where lambda is not too small, something like 0.5. And what it does is that the values are encoding the index of the best arm. If the best arm is 1, it's 0, 0. If it's 2, then 0 lambda. If it's 3, lambda 0. If it's 4, then lambda lambda, okay? So this is binary encoding. So now you can see that this is sort of the generalization of the previous fruit example to coding, right? So if you're smart, you don't want to pull this arm 1 to 4 to identify which one is the best, the true hypothesis, because the mean values are close to each other. You want to pull those cheating arms, because once you identify, right, you collect samples and sample mean will converge to the true mean. So at some point, you can be very confident on which one is the best arm. And once you become confident, then you can start exploiting those arms and then obtain large reward. So exactly this is what is obtained by lower bound. So lower bound, if you compute that gamma variables will only assign non-zero values for the cheating arms, okay? And the lower bound objective function value at the optimum becomes something like log 2k times log n. Compare that with what you would get with UCB. UCB will give you k over epsilon log n. So there's an exponential gap in the number of arms, but also epsilon is very small number. And so this 1 over epsilon will be larger than 1 over lambda squared. So there's a huge difference between achieving the lower bound or not. Okay, so this is an important example that we will come back.
Yeah, can I ask a question? I guess you haven't explained why you have the game is the 1 minus epsilon, 1 plus epsilon. So starting at f5, 1 plus epsilon starts to appear. What's the role of that?
Oh, yeah. Sorry, yeah. Imagine just you have all the combination of 1 minus epsilon, like imagine all the combination of these values, right?
Right.
Yeah.
So why do you need the 1 plus epsilon as well?
Yeah, it's because if you want to talk about log n regret, you need to introduce this competing hypothesis, and yeah. So at some point it was needed, but yeah.
And is it important to have a finite number of hypotheses for this to make sense?
No, not for this example, but for the algorithm that I propose, it will be important. Yeah, because I rely on finite hypothesis.
Right, I see. All right, cool.
So yeah, you can imagine just a standard K-arm bandit setting with extra arm, right, with the cheating codes. That's always possible. Okay. Great. All right. So finally, let me mention other function classes that will become important. So I already talked about this competing hypothesis, but there are other two classes. So first one is docile. So docile is those when F4 is F star. These are the ones that predicts different mean values for the best arm. So that includes this gray, green, and yellow line. Okay, they're predicting different rewards. And these are called docile because this is really easy to handle, because once you roughly moderately confident about this F star, and then you start exploiting and you start pulling arm one, then just doing exploitation itself will provide statistical evidence against those docile hypotheses. So indeed, in the regret, they contribute to constant term. Okay, and finally, we have this equivalent class. Equivalent class, those are the ones that support the same best arm and the same reward. So here, this purple line, this is the equivalent. This is the one that belongs to equivalent class. And within a few lines, you can actually show that these three are disjoint, and they partition the entire function class. Okay, and one thing to note is that although equivalent class seems not that important, there are cases where this can incur that log and regret. So I'll talk about that in later slides. So this is pretty much some basic backgrounds that we need. So let me pause at this moment and see if there's any question.
Well, there are not really any questions in the chat.
Okay.
And to me, it makes perfect sense. Wait, so, okay, so John Lee is asking if you can explain a little bit about this equivalence class again.
Oh, yeah.
Yeah.
Okay, this is the one. So this is parameterized by the true hypothesis F star. So given F star being F4, let's say, okay, the best arm is arm 1, right? And the mean value it's predicting is 0.75. Equivalent class consists of those functions or hypotheses that places the same best arm and with the same mean reward. So that's exactly this purple line, okay? Because this purple line, it believes that the best arm is 1 and the mean reward is 0.75.
And also the blue. Also the blue, right?
I'm sorry?
The blue as well. Well, yeah, okay, the blue was the optimal. Okay, sure.
Oh, yeah. Sorry, you're right. Yeah. It's optimal, but in this classification, by definition, yeah, it's in there. Yeah.
It's in there, yeah.
Yeah.
Oh, yeah, right. It's not competing, it's equivalent. I see.
Yeah.
But maybe like equivalent is a little bit misleading because it's
I see.
in every sense, so maybe this
Yeah,
can be confusing.
Right.
All right, great.
Okay.
Thank you.
No other questions? Then let's talk about crop. So how do we handle this issue? So we follow pretty much the line of optimism, where we construct a confidence set. Okay. So the way we construct confidence set is that we define a cumulative loss function, right? So this is cumulative loss measured in square loss. So recall that AS is the arm that you pull at time S. RS is the noisy reward that you receive. So you're measuring how far this F is predicting from the noisy reward that you received. And the script FT, that's the confidence set. So this is just measuring how far you are from the ERM. And there's a threshold we use, which is beta T. That's of order log T. Okay, but let me mention that this is implying the confidence level of 1 minus polynomial of log 1 over T. In the paper, it is actually 1 minus 1 over T squared. And there are 4 important branches, so let me explain one by one. Exploit, feasible, fallback, and conflict. First, for exploits, we just ask does every F in the confidence set supports the same best arm? Right? If they all unanimously agree on the best arm, then we're very confident that that's the best arm. So we just pull that arm. So this is exactly doing exploitation. Now, if that's not true, then we enter a feasible case. And this is where we compute the pessimism, denoted by FT bar. And this is the one among the confidence set, the one that minimizes the largest mean predicted by F. So this should remind you of the optimism, which replaces minimum with maximum. And then we're going to use this pessimism to invoke that optimization problem and solve it and say this gamma star is the solution of the optimization problem. And then we do something called tracking. So what we do is that we look at the arm pull ratios of the current sample count of each arm. And then you compare that with the solution gamma star. And we pull the one that's most offending. Okay, so the goal here is to try to match your count to the gamma star. So let me then talk about why this pessimism is what we are choosing. So here's a little example. We have 3 hypotheses, okay? And I'm both facing the best arm. The underlined ones are the informative arm, meaning that they will receive non-zero gamma value, okay? And it's easy to see that for F2, you can use arm 4 to eliminate its competing hypothesis, which is F1, right? Because there's a large gap. So here's the question, right? So at the beginning, we have all F1 and 2 and 3 in the confidence set. And if I knew F star, I could track gamma of F star, but we don't know it. So which one should I track? So here's my claim. My claim is that we should follow pessimism. So consider case by case. What if F star was actually F3, right? That's the true one. Then, of course, following the pessimism. So currently, pessimism is the F3, right? Because it's predicting the smallest, largest mean. Okay, so following F star will give you, will do the right thing, of course. Now, what if F star is actually F2? Well, then we still follow the informative arm of F3 because we're tracking. And then we'll pull arm 5. But then the sample mean will get closer to 0, not 0.25. So at some point, we can be confident that F3 is not the true one. So we get to reject F3 from the confidence set. Now we only have F1 and 2. And if you compute the pessimism, it becomes F2. Okay? And so now again, pessimism becomes the F star. So by following pessimism, we either does the right thing or you eliminate yourself and you find another pessimism. Now think about this. What if we didn't do that, right? What if we have F1, 2, 3 in the set, but we decided to follow the informative arm of F2? Well, then we will pull this informative arm 4, but that's not going to eliminate F3 because F3 actually predicts the same mean reward. Okay, so you get stuck at pulling A4 for a long time, but both hypotheses receive the same loss. Okay, so you don't get to eliminate, you get stuck. And if you use ERM and follow the ERM, then at the beginning, the issue is the same because at the beginning, ERM is pretty unstable, and with constant probability, it may be F2, and you get the same situation. Okay, so the idea, at least in this example, is that the lower bound constraint prescribes how to distinguish F star from the competing set, and the competing hypothesis will have higher mean rewards. Okay, will support higher mean rewards. So I'm going to set pessimism and track them, and that means all the other hypotheses will appear in the constraint set. If I follow F2, F3 will not appear in the constraint set because that's not competing hypothesis to F2. Okay, so that's roughly the idea behind pessimism, but it doesn't always work. But I don't know if there's any question at this point.
So just to recap this example. So the reason choosing F2 is bad is because F3, if F3 was actually the true hypothesis, it's not competing with F2 because the optimum value for F3 under F3 is smaller than under F2. And therefore, you're never going to pull A5, which would otherwise reveal that the true function is F3. Okay. So it's because we use this optimum design, which says that you should only consider the competing hypothesis. So you have this bi-level thing, and you have to think about that. Okay.
So yeah, that's, right. Yeah, that explains well. Yeah. Okay.
So I have a bit of a more basic question regarding what you mean by tracking exactly.
Oh,
I sort
okay.
of missed that part.
Oh, sorry. Yeah. So tracking means, you're trying to make your arm pole as close as possible to the gamma A star. So in this case, gamma A star for F3 is non-zero for A5 and 0 for all the other. So by tracking, you will just pull arm A5 if you're tracking F3. It's trying to match with gamma.
Yeah, so I suppose my question is like even a little bit more basic than that. So like, what is exactly the meaning of tracking that that you mean here? It's like you're trying to match the empirical distribution of past arm draws with gamma star.
Yeah.
But why does the argmin do this, and why not the, I don't know, argmax or something? I guess like any mismatch.
You're underpulling target, and then you want
Right.
Yeah, right.
Right.
I see. Right. So just trying to spot the arms that are underpulled under gamma star.
Yeah.
Trying to bring those up to that. Right. Okay. Yeah, maybe this is a standard idea in this context.
Oh, no. Yeah, I should. Yeah. It's exactly right. Yeah, you are trying to pull arms that are underpulled when compared to the gamma.
Right. Okay, I get it. Good.
Okay, great. Okay, so that's the basic idea of pessimism. But if you work through examples, you'll find an example that you will get stuck. Okay, and that's due to the presence of docile hypothesis that predicts higher mean value than the current pessimism. And here's an example. Okay, it's a similar example. Here, F2 is a pessimism, and say, even that's actually true one. But I can add this one, right? So this is non-competing. This is docile hypothesis because with respect to F2, it assigns a different mean value to the best arm of F2. Okay, but it assigns exactly the same value for that informative arm. So again, you get stuck. Or similarly, it may not even exactly same, but it may be something like very close to that informative arm's mean reward. So it'll take incredibly long time to reject F4. So in this case, just following gamma is really not a good idea. So we should do something else. And here's what I propose. Okay, this looks scary, but let me not go into a lot of details. Like lots of details are not so important. The important part is that I further add in the docile hypothesis in the constraint. And those that have predicts higher mean value for the when compared to the F. In this case, this is pessimism. Okay, so this idea is just to make sure that we will still make progress, right? We want to not get stuck. Okay, so that's it. Like there's nothing else really special. I'm just adding in the docile hypothesis into the constraints. So now, but then we have to draw a line. Like when are we going to follow gamma, and when we're going to follow psi? Okay. And so here's something to set up to talk about that. So first, you can imagine this set of pairs of best arm index and that best arm's mean reward. Okay, you can collect these pairs for every single hypothesis in the confidence set. And then this naturally induces a partition of f of t by collecting those that agrees on this pair. So here's the pictorial demonstration here. We have arm 1, 2, and 3, and the mean rewards in the y-axis. And each block is a set of hypotheses that agrees on the same best arm and the best mean. Okay, this is sort of the equivalence class that I talked about before. So now, given that, we can define optimistic set as the one that contains the optimism. Okay, so in this case, this has the highest mean reward. So that's the optimistic set. We can define pessimistic set. Pessimistic set is the one that predicts the smallest, largest mean reward. And now, with this knowledge, what we're going to do is we're going to use gamma of the pessimism if we can satisfy this similar information constraint that we saw from the lower bound for all optimistic set hypotheses. Okay, so the idea is that even if there are docile hypotheses in the optimistic set, if gamma alone can eliminate them, then I will just go for it. But otherwise, I will fall back to psi. Okay. And then we can see that we never get stuck. Okay, so this is how the algorithm is called crush optimism with pessimism, right? You have this upper and lower envelope, and you're using pessimism to eliminate the optimism. If successful, that will be eliminated, and then the envelope becomes smaller. But then it may as well, by trying to eliminate optimism, it actually could end up eliminating pessimism, okay, like we saw before in the example. So you see, it's kind of like you have upper and lower sort of envelope, and it's kind of squeezing together. And then eventually it'll either identify the class that contains the true one, or we identify enough that all the hypotheses are recommending the same best arm, at which point we can just start exploitation. Okay, makes sense so far?
Yeah, it does. I mean, so there was a question in the chat that which is about well, how do you choose the docile hypothesis? Which, let me just rephrase that as, docile is defined with respect to some f star, right, or some conjectured f star, and here you use this pessimistic choice of f bar t for defining the docile hypothesis. But could you use like something else and would end up with something that still makes sense?
Yeah, I thought about it. You could do something else. I guess this is one simple choice.
Mm-hmm.
Yeah, now that we're using this psi, like you can choose whatever, and still if you use psi, it'll do a reasonable job. Or you can modify the optimization formulation. And I guess this is one choice that I made. I found to be simple.
Yeah, it makes a lot of sense to me, especially with this crushing explanation, like that one.
Okay.
All right, that's good. Thank you.
All right. So incorporating that idea, now we're expanding the algorithm. So now it's crop version 2, and so we do check if the gamma based on the pessimism is sufficient to eliminate the optimistic set. Then we do set pi t to be gamma. Otherwise, we set pi t to be psi, and we do the tracking. Okay, so now with this, for many cases, you can get the asymptotic optimality within a constant vector. But there's one thing that remains. Okay, so here's the issue. It's quite tricky issue. Look at this example. We have F2 and F3. Both can be pessimism. Okay, they have all the same mean reward up to arm 4, but it's just different at the arm 5. So now you face this challenge, right? Okay, they support both the same arm and supports the same reward, but which informative arm you should follow, right? So if F star is F2, of course, let's say we follow F2, right, and pull arm 4. If F star is F2, then of course this is the right thing to do. But otherwise, you are going to pull a suboptimal arm, right? The most informative arm is A5, right? Has the highest gap. Okay. So the effect is that you will still get log and regret, but not with the optimal constant. Okay, and that's a problematic thing. And we can adjust this, play with this number to make that suboptimality gap to be arbitrarily large. So we have to do something. Actually have to distinguish between these two. Okay, so here's the solution that I think. So imagine, recall that in the standard bandit, we use the confidence level. I briefly mentioned the confidence level. We use confidence level of 1 minus 1 over n, roughly speaking, because when the confidence set fails, we get linear regret. Okay, so now you can do the similar reasoning. If you miss identifying this F2 and F3, then we get log n regret, although it's a suboptimal constant, right? So then how much should we be confident? Okay, that's just pattern matching problem. I'll give you a few seconds to think about it. And so, yeah, so just do pattern matching, I want to be 1 minus 1 over log n confident, okay? So the solution that I'm thinking is to distinguish F2 and F3, I'm going to construct another confidence set whose confidence level is like 1 minus 1 over log n. So how do I do that? So let me just not go into every single detail here, but we do end up constructing a refined confidence set that resides in the pessimistic set. Okay, so among the pessimism, if there are conflicting recommendation on gamma, I want to distinguish. So eventually this is refined because, this is belonging to the pessimistic set, and that pessimistic set is again belonging to the confidence set. And, this confidence level is instead of log t, now log t. And precisely the confidence level becomes polynomial of 1 over log t. And so idea is at every step, we compute that gamma value for every single member in this confidence set, refined one. And then we ask, do they all agree up to constant scaling? If they do agree, we just continue with the previous version of the crop. Otherwise, we do something else. So this is another version of the optimization problem, but it will just have one difference, that it is trying to distinguish from those conflicting advice, okay? So this is involving the equivalent class. And so let me not go into much detail here, but this is a much tighter confidence set. So this is the final version of the crop. We first check if there's any conflicting advice. If that conflicts, then we set pi t to be phi, okay? And then other things are already explained. Okay, so that's the final version. And yeah, so that's the end of algorithm. Any questions so far?
Well, I guess the specifics are probably boring, but like, what do you mean that they are not proportional to each other?
Oh, yeah, right. So in fact, sorry, it's already there. So, okay, not proportional to each other. They are same up to constant factor, right? If you were to divide gamma of f and gamma of g, then their ratio is always the same.
Oh, yeah, right. Okay. Right.
Yeah, because eventually we just use the ratio in the tracking, so it doesn't matter if it's just constant scaling.
Oh, I see. Okay. Sorry, that was a dumb question. Yeah.
Okay. If there's no other question, I'll proceed.
There is one more question. I'm just trying to understand the question. Kishan is asking, since F2 equals F3 in slide 21, can we disregard such cases? I got a bit confused about the question.
Yeah. Yeah, I don't know what
here.
Yeah.
F2 is not F3, right? Like
yeah, it's different, right? Yeah, it assigns different mean reward for the ARM5.
I guess maybe what's meant is that the optimal value under F2 and F3 are the same. And so it doesn't really matter whether you're in F2 or F3 cases. So you don't need to distinguish between them.
Yeah, I can answer, yeah. Okay. Yeah, so what matters in the regret is you want to minimize the number of arm pulls of non-best arms. Okay, the cost is incurred whenever you pull some other arm. And here, so the thing about Bandit is that you have to be like increasingly confident. So actually, if you construct a confidence set, then once even if you eliminate this competing hypothesis F1, it's going to keep coming back because your confidence level is increasing and your threshold that we define is actually increasing, right? It's increasing over time. So even if it was rejected before, it can come back. And that's the thing about the competing hypothesis. So you have to repeatedly use those informative arms to eliminate F1. But if you're using incorrect one, then you get suboptimal constant in the regret because you have to pull more if you pull arm 4. But arm 5 is more efficient.
Okay. Yeah.
So the hypotheses are like, sorry, yeah.
So how much you lose because you pulled an arm, and also how much information you gain.
Yeah, exactly.
Properly taken into account, and then that's, in this case, if you don't care about this distinction between F2 and F3, then you pay a higher constant cost because of this. And as you explained, the log n is coming from because you need to guard against F1, like time to time, like you have to go back and revisit the idea that, oh, maybe it's still F1. And then you reject it, and then for that, you want to be optimal.
Yeah, exactly. And the difference in the suboptimality gap can be made large enough if you just play with these numbers. So, okay, great question. Okay, so I have 5 minutes, so let me just point out some important stuff. So the main result, we have 4 terms. Here we have this effective number of arms. This is just counting how many arms will have non-zero psi value for at least one F. Okay, so in the cheating code example, this becomes log k. And we have this 3 other terms. One is log n term. Of course, that's the P1 is the one that appeared in the lower bound. The second one is something from conflict, and that's of order log n. Third one is log cardinality of F. And that's mainly from this psi, so it's from fallback case. So here's a corollary. Whenever P1 is 0, you can show that P2 is also 0. And so your regret bound does not scale with n, so we get bounded regret. So what happens in the cheating code? Well, the k of psi becomes log k. If you use crop, then we do have this rate, log k times log n. If you use forced exploration, you have plus k as the next term. And so you can easily imagine k being something exponential in d for some d, and say n is equal to k, then the regret of crop is d to the d squared, but the regret from forced exploration based algorithm becomes 2 to the d. So there's an exponential improvement. Here's a lower bound. Let me just skim this quickly. But recall that uninformative arm is those arms that receive 0 from the lower bound. Okay. But what lower bound says is, well, it's if you were to divide that expected number of poles of that uninformative arm by log n, that goes to 0. So it only tells you that that quantity up there is just something slightly smaller order than log n. So we don't know if we can actually pull constant number of times, or we have to pull something like square root of log n. So the question is, can we achieve asymptotically optimal regret, but at the same time pull all uninformative arms like constant times? And the answer is no. Okay, this is not in the paper currently, but we will update it in the archive in a few days. We can find an instance where there is an uninformative arm. You have to pull at least log n times, where this constant is some instance-dependent quantity. And the instance that we find is exactly the one that I showed you. That there's a conflicting advice. You have to really pull certain arms growing number of times, right, log n, to be able to distinguish between these 2 different advices. Okay, so let me see. Let me skip that one. But here's something I want to mention. The regret of UCB is actually minimum of this first one, n epsilon n. If you're not familiar with this, imagine n is something like 10. But if k is like million and epsilon is like 0.0001, then you can see that this is already very vacuous, right? Because if you restrict your mean reward value to be between 0 and 1, then after 3 steps, the maximum regret you can occur is 3. But this is like enormously large. But you can actually look at the behavior of UCB, and in this instance of the cheating code, because they pull base arms only, at each iteration, your gap, reward gap, is only at most epsilon or 2 epsilon here. So you have this, you can actually characterize regret of UCB as minimum of those 2 things. So first, it grows linearly, but with very small constant, epsilon. And then at some point, this first one becomes achieving the minimum. Now, if you were to run asymptotically optimal algorithm, right, those gamma star that's prescribed by the lower bound and play according to that. So in this case, this corresponds to just pulling cheating arms only, and then identify the best arm, then you play that one. If you do that, of course, the first one is smaller, but the second one becomes n. And the reason is that whenever you pull cheating arm, those are not so much reward efficient, right? They're either reward gap of 1 or 0.5 if lambda is 0.5. So in fact, if you just do that, then you can actually achieve linear worst case regret. And you can graphically see that there is a regime that following this oracle or the asymptotically optimal lower bound thing is going to be suboptimal than UCB. But this is a very intuitive thing, right? If you have limited budget and if you don't think you can confidently identify which one is the best arm, you might just go with epsilon optimal arm, right? If I plug in epsilon being 0.0001 that I was using before, 1 between 0.9999, I mean, that's like really nothing, right? So why not just pull this near optimal arm, right? That's very intuitive thing to do if you know these numbers. So ideally, we want to achieve best of both worlds, right? We want to have the first term of the asymptotically optimal algorithm, but for the second one, we want to have epsilon times n instead of n. In other words, we want to achieve minimum of those 2 curves. Can we do that? And we show a preliminary result in the paper that yes, if you know epsilon. And the idea is really simple. Up to this point, right, that's the transition point. Up to that point, you just run UCB, and you can run asymptotically optimal algorithm after then on, and you get like constant factor of this minimum. But of course, it's an open problem to how to do that without knowing epsilon. Okay, so just to summarize, we propose crop is asymptotically optimal within a constant factor, and it adapts to bounded regret. And it has improved finite time regret, especially with respect to the number of arms. Okay, we provide considerations when avoiding forced exploration, right? So we have to take care of the the docile hypothesis and some of the conflicting hypotheses, right, that belongs to the equivalent class. And previously those are all handled by forced exploration, but we kind of carefully look at which one are needed. Finally, we reveal some danger of naively mimicking the oracle or this lower bound, right? Because we may suffer linear regret in the finite time regime. So some of the interesting questions for research, of course, attaining worst case regret simultaneously would be interesting for a particular family. And we can try to extend the pessimism for linear bandits or ellipsis bandits and other similar structured bandit problems. But even more bigger question is, computing this optimization problem is really cumbersome. So can we find a way to not solve optimization problem? Maybe there's certain condition you can follow that eventually lead you to those asymptotically optimal regret. Another one is that we really need to think more about what is the lower bound for the finite time regime for with respect to the instance-dependent regret, right? This is largely not so much understood, especially because in the stochastic bandits, log n becomes dominating term. So people tend to focus on that too much, right? And then they do something else where there's large factor times slightly lower order than log n. So this clearly is not going to work. Like, we have to understand what's the right thing to do for the finite time regime. And finally, one thing I did like about the forced exploration-based approach is that you don't need to construct a confidence set, right? You have this optimization problem. Ideally, you know how to solve it. I mean, presumably, at least you can write down, right? And then you just add in force sampling, and it kind of works. So, but this approach that I propose is still relying on confidence set. And in many practical cases, whenever you have a new structure, you have to come up with new confidence set, and it has to be tight. And this is something to be improved, right? We want to just do something automatically whenever some structure or the reward model is given. Okay, so yeah, I guess that's it.
All right, very much. An applause. Right, thank you. That was wonderful. So we had like a bunch of questions. Let me just see if there were some other questions that were not asked. So Sharon was one. He had like a bit of a clarifying question regarding the algorithm, which I guess could be interesting. So like Sharon, can you ask your question if you're here?
Hi, Kwang. I was with you until slide 19, and then I got a little lost.
Okay.
So let's see. Okay, yeah. So at this point, why will we never get stuck?
Oh, yeah. So because either, I mean, yeah, we are following this either gamma or psi. And, if this condition is, I mean, either direction, right? Whether we use gamma or psi, because we are looking at this condition, this gamma, like whenever this constraint is satisfied, then following gamma will efficiently remove those that appear in the lower bound constraint, right? Those competing hypotheses and those optimistic set. I mean, these are the sort of efficient armful to make to eliminate the optimism. Or maybe there's something else that I missed.
I guess maybe the question is rather than if you do the fallback, why that doesn't generate a lot of regret?
Yeah, the case you will fall back is the case where there are some docile hypotheses in there, and removing docile hypothesis only result in constant term in the regret bound.
Yeah, so there you have to use this partitioning idea that you had at the beginning, right? That you have three types of things, either this or that or that, and then here you're gonna just like rely on that and say that like if we are not in this case, then we are in this other case. And look, in this other case, the optimal arm is the same, so you're not suffering extra regret because of that.
Yeah, so eventually
value is the same. Sorry, the optimal value is the same. Yeah.
Yeah, eventually what affects the log n is the case where it's sort of so there's like two stages. At the beginning, it's like non-steady and you have no idea what's f star. But after a certain point of time, there's a regime where you're pretty confident, moderately confident about f star. And at this steady state, you face this stage where you're like either exploiting, right? Because all the hypotheses are recommending the same best arm. But occasionally you get this competing hypothesis coming back, and you're eliminating those with the informative arms, and that's what causes log n regret. And docile hypothesis will never come back because by definition, whenever I do sufficient exploitation, it'll automatically eliminate it, and they will incur large loss in the confidence set, so they never come back.
Yeah, I see. Okay, yeah. Yeah. I get it. Yes. Okay. Thanks.
All right. So there's another more specific question about the bound itself in theorem 1. If you go to slide 25. Then I guess the question is, right, so you have this log n terms, which is multiplied by P2, which is from this conflict part that you explained last, yeah? I'm just trying to like interpret the question and also sort of answer it partially at the same time. So I guess the log n comes from the sort of smaller confidence set that you have for this part. Yeah. So I think that was like fairly well explained, but I have rather a question about this P3 bit that has this log f term in there. So can you explain where that comes from? Because I'm not sure I got that exactly.
Yeah. So it's actually right. So whenever we construct confidence set, we do have like log cardinality of f. And in fact, some detail I didn't explain that actually I'm setting aside to at least have achieved maximum of gamma and p. So they're like covering those things. And so actually lots of things, like actually P3 actually includes P1 and P2.
Right.
Because like, the confidence level thing kind of appears in the, this logarithmic term, but the log script f cardinality times n, so I'm just separating out to plus, but then it brings in the factor P1, right? But then, I'm pulling everything together in the P3.
But then is it fair to say that this log f comes from just taking a union bound over all functions?
Oh, yeah, it does, yeah.
Just implies the question, can you improve this to, I don't know, some BC dimension or some other notion of size?
Yeah, absolutely. I think there's lots of tools to deal with, right? The covering number and all that good stuff. So, yeah. I didn't try personally, but yeah, I know the tools are out there, so.
Right, I see. So you could totally just take a covering of f and work with that through the algorithm. Yeah, but you still need to know what f is, and you still need to be able to cover it sort of nicely.
Right.
Right, and now I guess Csaba is going to ask about realizability.
Yes, I can ask about realizability. I guess that's a logical next question. Although I was still wondering about the covering argument, like how would it work? Maybe you have to use some non-uniform covering or whatnot, because maybe you have to refine the covering as you go, like localize it, something like that. Yeah, but like, okay. So did you think about the unrealizable case?
I haven't thought much about it's I mean, it's something that we should resolve at some point, right? But yeah, I don't know. What do you think about the agnostic case? I mean, there was a lot of work from MSR in New York and the Yahoo before, like on the the agnostic bandits in the conceptual case. Yeah, I mean, the algorithms tend to become like really monster. So yeah, I don't know.
There is a new paper by Dylan and Sasha, which is closer to this work, because either you work with a policy class or you work with a reward class. So here you're working with a class of reward functions.
Exactly, yeah.
And then you're kind of resorting to some kind of a regression oracle. I guess, yeah, like.
Yeah, but here, well, this is not a contextual bandit problem, right? So it should not be that complicated to deal with this agnostic case, right? So you can always do UCB, right? So you can always just recover the standard UCB guarantees. The question is, for example, like one formal way to ask this question is that if f is not really in the function class, can you still keep the UCB guarantee that holds for like general function classes? And actually get your faster rates that you have in this paper if f is within the function class?
Yeah, that's a great question. Yeah, sorry, yeah, I guess in this setup we assume finite hypothesis class anyways. So yeah, it's
Yeah, so I guess like the natural question is this algorithm going to be a complete disaster if
Oh, it is, I think.
yeah, it will be, right? So because we are totally relying on the structure information, I think if you do agnostic, then you do need to pull, you probably do need to do some sort of force exploration kind of thing, right? Because otherwise, you know, there's a million arms, but there's just one arm just behaving really, you know, differently from the structure, then you're screwed. So
You can be optimistic though, but increase somehow the confidence set, or like increase, you know, like if you're like inducing values, range of values for the arms, then you have to up it up.
Yeah. Yeah, interesting question. Right. Yeah, I thought about the agnostic case last year for a couple of weeks, and then yeah, I was clueless. Yeah.
Maybe someone else in the audience is gonna pick this up. We do have a bunch of questions on YouTube, by the way. So that is the obvious question of how strong is the assumption that the optimal arm is unique? I guess you mentioned that you can remove that assumption, but is there a price? Is there something non-trivial that you need to do?
Yeah, it's just that lots of definitions should do the tie breaking carefully. So that's one sort of cumbersome part. Yeah, it's like we have to first fix the definition of equivalent class, because yeah, multiple arms are, you know, I mean each hypothesis can put more than one arm as the best arm. So the function classes becomes, you know, requires a little more care, and I guess the algorithm will have to do some sort of tie breaking carefully. It's yeah, we didn't like arrive till the end, but we thought about a little some preliminary examinations, and it didn't seem like too detrimental. But yeah.
YouTube is asking whether it's realistic to assume that you have finitely many hypotheses. Just a construct.
Right. Yeah. I would say it's not realistic. This is just you know, you often think about simpler problem, but it gives you some more insight. So that was my intention.
Yeah.
And I do feel I learned something, but you know, we have to get it, see if the idea extends to the more complex hypothesis class.
Yeah. So this is a step you think in the right direction, sort of work. Yeah, I think that this is pretty important actually. Just sometimes you have to simplify things, and then you get some insight, and then from there you can take it to the next level.
Yeah. Yeah.
Okay. Isn't it very improbable to encounter some intricate relation between hypotheses like binary encoding in real life? Oh, okay. That's a good question. Like, isn't it like you know, the structured class? Like, how realistic is that you're gonna have like finite regret or anything like that?
Sorry, I'm not sure if I understood the question.
So is it like, do you expect to see any kind of real examples where structure can help you to non-trivially reduce the regret compared to, let's say, UCB? I guess that's the question.
Yeah, I mean, there are lots of things. For example, if you look at causal bandits, so causal bandits, they use the structure causal information to impose the structure, and you can use structure to provably perform better than UCB and other stuff. There's a bunch of papers on this. So
I guess I add to that we have this beautiful framework of partial monitoring, right? which is really like decoupling information and reward. Special case of that is bandits when they are coupled.
Right.
And there the structure is more obvious. And in a lot of real-world examples, you can expect that you're gonna have some side observations, like you pull an arm and then you observe a bunch of things that are related to the reward, and maybe you also observe the reward, or maybe you don't observe the reward. And then if you have all this rich structure, then I think that anything can happen.
Right. Yeah. Yeah. That's a good point. Yeah.
And so I like to think about this structured bandit problem as a special case of that, when things are tied together.
Right.
And it's quite interesting that like how you work out the details of that.
Yeah, but I guess like already this fruit vendor example is like a good one to motivate this kind of setup in which, well, optimism may not always work well. There may be definitely suboptimal actions that can tell you a lot about the user that you want to implement.
Yeah, I think this idea of using informative actions, it's like it's not going to go away, and it's realistic to assume that you can have something like that.
Yeah, like the cheating code example, I was thinking of something like, we have not just the ARM features, but also we have some expert opinion on which one is the best one, right? Maybe we have an expert who does not know exactly what reward is going to give to us, but the expert opinion more often like accurately give you like which one is the right one to do. So yeah, but I think it is important to see whether you can actually find those examples in the real world data sets. I think that would be interesting.
Yeah, so I guess the thing is that your problem can have this structure secretly somewhere in a way that is not really obvious if you just look at it yourself. But if you just solve these optimization problems with respect to like whatever candidate solutions, then this structure is going to reveal itself in a way that is very difficult to explore in a naive way.
I guess this whole thing is about like bringing in bias, like in a proper way.
Yeah.
Explanation method. Oh, and what about reinforcement learning? Like, isn't that this case where you have some extra structure like MDPs, whatnot, and we are not doing the best to exploit that structure, maybe?
Yeah, that's what I think too. Yeah, yeah. There's a paper on doing the ergodic reinforcement learning setting. Like it's not episodical, like you just keep going on. And yeah, in this setting, like a similar thing was done, and you get also this logarithmic regret lower bound that looks just like this, but it involves all sorts of states and so on. And yeah, so I'm trying to find the reference there. Yeah, there's
right,
the Jungzul Oak and Alexander Ploutier.
Yes.
Paper. And yeah, so I think there's some opportunity here, and you can imagine the case where the benefit of informative arm becomes more exaggerated if the variance of each arm is different, right? What if the variance of lemon is like small, right? Then it'll help you a lot. And I don't know if it's something that naturally happens in like generalized linear model. If you consider binary rewards, even if the reward is 0, that variance is really small. So I presumably that should be really helpful. Yeah.
Right. So Sharon had another question. Sharon, are you going to ask this question?
Sure. So Kwang, I remember we were speaking once that we should incorporate like pure exploration algorithms into the thing so that at least we pull arms which give us like higher information gain and then trade them, like do an epoch type thing. And can we use something like that to get like basically the same effect you're getting here?
Yeah. So that was a rough idea. I don't know. Yeah, I haven't thought much more along. Yeah, it's just that if you, I think there's this regret lower bound if you are not adaptive about, like there's this in this bandit algorithms book, there's an example where you can do explore then commit in a sort of in a way that, like, can you find the universal threshold after which you just do exploitation, and like you can find that, but that kind of gives you like n to the 2/3 regret instead of root n in the worst case. And I think given that result, seems like it's going to hurt the regret. But I don't know. It depends on how you actually implement that idea, right? So the idea is like maybe you can use machinery from pure exploration, and then do exploitation and some sort of like reduction way, right? You take in any pure exploration algorithm, but you have some systematic way to use it to perform bandits. I guess it depends on how you adjust the confidence level, but yeah, I don't know. I'm just talking random stuff.
Yeah, I mean, it's tricky. Okay, anyway, thanks.
Yeah.
All right, cool. So I guess this is like time to stop recording and for people to ask their nastiest questions.